There are roughly 200 billion stars in the Milky Way galaxy, and orbiting just one of them, one ordinary, unremarkable yellow dwarf star, 2/3 of the way out from the galactic center. On one small rocky planet, a species recently figured out how to split the atom, send radio waves into space, and argue about whether or not it's alone in the universe. But in 1960, a physicist named Ronald Bracewell asked a different question. He didn't ask whether alien civilizations exist. He asked if they do exist. If even one civilization anywhere in this galaxy developed technology a million years before us, what would be the smartest way for them to explore the cosmos? His answer wasn't radio signals. It was machines. Small, autonomous, self-replicating machines launched once and then left to multiply across the galaxy on their own, spreading from star to star, watching, recording, waiting. Bracewell calculated that a sufficiently advanced civilization could fill the entire galaxy with these probes in less time than the Earth has been alive, which raises a question that, once you hear it, is hard to stop thinking about. What if alien probes are already here, in our solar system, in our orbital neighborhood, perhaps within a few million kilometers of Earth, and we've simply never looked? No alien probes have ever been found, but the scientists who proposed this idea weren't fringe thinkers. They published in journals like Nature and the Astronomical Journal, and their math is uncomfortably hard to dismiss. Today, we're exploring one of the most scientifically credible ideas in the history of speculation about extraterrestrial intelligence already being present in our galaxy. No alien probes have been confirmed or discovered, but the theories are real, the math is real, and the questions they raise are worth taking seriously. Let's start at the beginning. In 1960, the same year Frank Drake launched Project Ozma, humanity's first systematic search for extraterrestrial intelligence, Stanford professor Ronald Bracewell published a paper that quietly changed the way some physicists think about interstellar communication. His argument was elegant and, in hindsight, obvious. Radio, he pointed out, the thing SETI was betting everything on, is a terrible way to communicate across interstellar distances. A signal spreads out in all directions. By the time it crosses a few light years, it's incredibly faint, diluted across an enormous sphere of space. Detecting it requires a receiver pointed with the right sensitivity, at the right frequency, at the right time, in the right direction. The odds are astronomical. Literally. There's a better strategy. Instead of broadcasting and hoping someone is listening, an advanced civilization could send physical probes to other star systems, small, intelligent, autonomous spacecraft that travel to a target star, enter orbit, and wait for centuries, for millennia, for however long it takes, until a technological civilization emerges on one of that star's planets. When that civilization finally develops radio technology, the probe detects their signals, activates, and initiates contact. Not from hundreds of light years away, from right next door, already in the neighborhood, already watching. Bracewell called these messenger probes. Today, we call them Bracewell probes. And the concept, while remarkable on its own, becomes something else entirely when combined with the work of a mathematician named John von Neumann. Von Neumann, one of the 20th century's most formidable minds, developed the mathematical theory of self-replicating machines, systems that could build copies of themselves from raw materials in their environment. Combine Bracewell's idea, autonomous probes sent to other star systems, with von Neumann's concept of self-replication, and you get something extraordinary. A civilization doesn't need to build billions of probes. It needs to build one. One probe travels to the nearest star system. It finds raw materials, asteroids, comets, rocky debris, and uses them to build two copies of itself. Those two copies travel to two new star systems. Each builds two more. And so on. And so on. Generation after generation, exponentially spreading outward from the home system. This is what scientists call a von Neumann probe, or when combined with Bracewell's surveillance concept, a self-replicating interstellar sentinel. A machine designed to spread, observe, and endure indefinitely without further instruction from its creators. Let's run the numbers. Assume each probe travels at just 1% of the speed of light, roughly 3,000 kilometers per second. The average distance between stars in our region of the galaxy is about 4 to 5 light years. So each probe takes around 400 to 500 years to reach the next star, add another 100 years for mining, manufacturing, and launching new copies. That's roughly 500 to 600 years per generation. With exponential replication, within about 50 million years, self-replicating probes launched from a single origin point could reach every star system in the Milky Way. 50 million years sounds like a long time, but our galaxy is over 13 billion years old. 50 million years is less than half of 1% of the galaxy's age. It's a cosmic blink. It's nothing, which means if even one civilization, at any point in the last 13 billion years, developed this technology and launched a single self-replicating probe, the entire galaxy would already be full of them. So, hypothetically, if self-replicating probes entered our solar system at some point in the last few billion years, where would they be? The answer, according to multiple scientific papers, is almost anywhere. And we'd have virtually no way of finding them. Location 1. The asteroid belt. Between Mars and Jupiter lies a vast ring of rocky debris, millions of asteroids ranging from dust grains to objects hundreds of kilometers across. A probe designed to mine raw materials for self-replication would find this environment ideal. Abundant metals, silicates, and water ice, countless hiding places, little sunlight on dark surfaces. We've cataloged around 1.2 million asteroids, but we've imaged only a handful up close. A machine the size of a car, attached to the surface of a tumbling charcoal-dark rock, would be virtually indistinguishable from the asteroid itself. Location 2, the Lagrange points. Every two-body system, like the Earth and the Sun, creates 5 special points in space where gravitational forces balance. Objects placed at these Lagrange points can remain there with minimal energy. Earth's L4 and L5 points, which lead and trail us in orbit by 60 degrees, naturally collect debris. We've already found at least one asteroid, 2010 TK7, at L4. Our surveys are far from complete. A dormant probe parked at L4 or L5 would enjoy a stable vantage point with a continuous, unobstructed view of Earth, watching for as long as it wanted. Location 3, the Kuiper Belt and the Oort Cloud. Beyond Neptune lies the Kuiper Belt, a vast population of icy bodies and dwarf planets extending tens of astronomical units from the Sun. Far beyond that, the theorized Oort Cloud, a spherical shell of trillions of comets stretching perhaps 2 light-years from the Sun. We've mapped only a tiny fraction of the Kuiper Belt. We've never directly observed the Oort Cloud. A network of probes could operate in these regions for eons, effectively invisible, distance and darkness providing perfect concealment. Location 4. Co-orbital objects and captured moons. The giant planets are swarmed by tiny irregular moons, many only a few kilometers across, seen only as dim points from afar. Jupiter alone has at least 95 known moons. Saturn has over 140. We've barely looked at most of them. Any one of these objects could host or even be something artificial. We simply don't know. And that brings us to the most unsettling point of all. The reason this theory is so disturbing isn't just that probes might be hidden in our solar system. It's that, with our current capabilities, we would have no way of knowing. We've mapped less than a fraction of 1% of the objects in our own solar system with meaningful resolution. We are, in a very literal sense, surrounded by the unknown. In October 2017, a reminder of that unknown appeared and then was gone. Astronomers using the Pan-STARRS telescope in Hawaii detected something unprecedented. an object passing through our solar system that hadn't originated here. It came from interstellar space, moving too fast to be captured into orbit. It was just passing through. They named it Oumuamua, Hawaiian for a messenger from afar arriving first. Almost immediately, it defied expectations. Based on its light curve, the way its brightness changed as it tumbled, it appeared extremely elongated, or perhaps flattened like a disk. Neither shape is common among known asteroids or comets. It showed no visible coma, no cloud of gas and dust, yet as it moved away from the sun, it accelerated in a way gravity alone couldn't explain. For comets, outgassing can act like tiny thrusters. But we detected no gas emissions of any kind. Something was pushing it, and no one could conclusively explain what. In 2018, Harvard astronomer Avi Loeb co-authored a paper suggesting a possibility many were reluctant to say out loud. What if the observed acceleration was caused by solar radiation pressure, sunlight pushing against a large, thin surface? In other words, a solar sail. If so, could Oumuamua have been an artifact of alien technology? It's important to emphasize, this remains a minority view. Most astrophysicists favor natural explanations. An unusual comet with undetected outgassing, a fragment of nitrogen or hydrogen ice, a novel but natural interstellar object. The scientific consensus is that Oumuamua was almost certainly natural. But Loeb's point wasn't necessarily that it was a probe. His point was that we never got close enough to find out. By the time we noticed it, it had rounded the sun and was already leaving. We had no spacecraft ready to intercept it. Everything we know about its shape is inferred from indirect brightness measurements. The first confirmed interstellar object ever detected in our solar system, and all we could do was watch it go. If it had been a probe, if it had been exactly the kind of sentinel Bracewell imagined, we would have had no way of knowing. Which brings us to a proposal that makes this entire conversation uncomfortably practical. In 2019, physicist James Benford published a peer-reviewed paper in the Astronomical Journal, arguing that if Bracewell probes exist in our solar system, they might not be broadcasting at all. They might be lurking, passive, quiet, dormant, waiting for a trigger, waiting for us to reach a certain level of technology, or simply waiting for us to notice. Benford suggested that the most logical place to look for such lurkers would be among Earth's co-orbital objects, small asteroids and debris that share our planet's orbit or pass near it regularly. These locations offer persistent surveillance with minimal energy. They are close enough to watch everything we do, and they are small enough to escape notice. Crucially, Benford's argument wasn't science fiction. It was a cost-benefit analysis, grounded in physics and engineering, published in a mainstream journal. He concluded that the most efficient way for an advanced species to explore the galaxy is exactly the kind of approach that would be invisible to us, unless we deliberately searched for it. And here's the key insight, the one that should bother you. We have never searched. SETI, the search for extraterrestrial intelligence, has spent decades listening for radio signals from distant stars. We have scanned the skies with radio telescopes, optical telescopes, and infrared detectors, hoping to catch a transmission from light years away. But we have never conducted a dedicated, systematic search for alien probes in our own solar system. In our orbital neighborhood, potentially within a few million kilometers of Earth. We've been listening for a shout from across the galaxy, while something might be whispering from right next door. The probes could be here. And we've never looked. Let's bring this together. The math says a single self-replicating probe, launched by a single civilization at any point in the last 13 billion years, could have reached every star system in the galaxy, including ours, billions of years ago. The theory says those probes would be small, autonomous, quiet, designed to observe, not announce themselves. The physics says they could hide almost anywhere, in the asteroid belt, at Lagrange points, in the Kuiper Belt, among the moons of Jupiter and Saturn, or drifting the dark beyond Neptune. And the reality is that we've surveyed only a tiny fraction of our own solar system, with enough resolution to tell natural from artificial. We talk about the Fermi paradox, the great silence, the absence of evidence for extraterrestrial intelligence. But maybe the silence isn't evidence of absence. Maybe the silence is exactly what a galaxy full of quiet, patient watching machines would sound like. Maybe the probes arrived before the dinosaurs, before the first fish crawled onto land, before the first cell divided in a warm ocean 4 billion years ago. Maybe they've been here for the entire history of life on Earth, watching, recording, transmitting their observations back to a civilization we can't imagine, across distances we can barely comprehend. Or maybe, and this is the thought that keeps certain scientists awake at night, maybe the civilization that built them is long gone, extinct for millions or billions of years, and the probes just kept going, kept replicating, kept watching, kept transmitting their findings into the void, long after there was anyone left to receive their reports, machines outliving their creators, filling a galaxy with silent eyes that see everything and report to no one. In our first video, we told a fictional story about SpaceX discovering ancient, manufactured debris in Earth orbit. It was fiction, but after everything we've discussed today, the Bracewell probes, the von Neumann math, the hiding places in our own solar system, the Oumuamua mystery, the Lurker Hypothesis, that story doesn't feel quite as far-fetched anymore. Does it?